Welcome back. In the previous session, we went through the first chain of thought behind minimum heaps, or rather binary heaps. It could be a max heap, but the idea is the same. So to recap, we went through how we were able to express a minimum heap using binary trees. And these binary trees have three properties. Let's quickly draw one again. In this case, let's have the root contain 3, its children containing two values that are larger than itself. And for this subtree over here, for 12, you also have some children that has values larger than itself. And to recap, binary heaps in this case, in the case of minimum heaps, there's three properties. The first property is that nodes have up to children, have up to 2 children. The second property is that this binary heap must be complete. So a complete heap means that all of the nodes at the front are filled up, and the binary heaps are filled up in a level order fashion, and all the nodes on the left side of each level is filled into the array first. For the final property, specific to minimum heaps, every single parent value should be less than or equals to its child values. So this is pretty much a recap of binary heaps. Now, previously we also went through how we were able to insert values into a binary heap by putting it at the very end of the binary heap over here. So for example, if you wanted to insert a value 1 in this case, you will insert it like so. And if you wish to express this same binary heap in an array, it will look something like this. By filling in the numbers in a level order fashion from left to right, the binary heap will look something like this. So where we insert a value at the very back of the heap, the first step is to put it at the very back, and afterwards what we will do is we will compare it with its parent. This operation is called sift up, because if this node happens to be smaller than its parent, what we will do is we will sift it up like this. And notice that even after one operation of sift up, that is not sufficient, because we can see that the minimum heap property is still not achieved between this newly swapped node and its parent over here. So we will recursively swap it until this node either reaches the top of the heap or the swap no longer happens. And when that happens, we have successfully inserted a node while maintaining the minimum heap property. So that was our previous chain of thought. Now, our next chain of thought is to figure out how do we remove an item from the minimum heap without disturbing the minimum heap property. So let's quickly lasso this binary tree below and put it here. So now, let's say we wish to pop the smallest element of this minimum heap. And in this case, as we can see, as per the minimum heap property, the smallest number inside your minimum heap is at the very top of your binary heap. And if we express it like so, 1, 12, 3, 15, 18, and 14, the smallest number is pretty much at the very start of the binary heap. So now, we will be exploring how to delete 1 successfully from this binary heap without disturbing the minimum heap property. The first step is to store this current variable at 1 inside a temporary variable. So let's define int temp, and we'll set this to 1. This temporary variable will be popped off the binary heap in a bit. And the next step is to override this topmost value with the number at the very back of your heap. So in this case, 14. So we will put 14 here, and we would pop this off the binary heap like this. And at this point, we're done with the second step. The third and final step is to perform an operation called sift down. And like its name suggests, it is the process of recursively checking this value with the smaller children of the two. So in this case, what we will do is we will compare 14's 2 children. In this case, there's 12 and 3. And in this case, since 3 is the smaller child, we will compare this value together with its smaller children. So over here, in this case, since the parent 14 has a larger value than its child, we will swap them as per sift down. So now we have 3 here and 14 here. And in this case, we are pretty much done because 14 has no more children. But let's say in a hypothetical situation, if you have another child over here, let's say 19. Okay, I guess let's swap it with another value that is smaller than 14, let's say. Let's call this, let's see, 4, I guess. And now we have 4 over here. What we will do is we will proceed to recursively check this value as well. And over here, we will see that 4 in this case is indeed smaller than the current value of 14. So we will sift down 14 over here. And that's pretty much it. And the idea is after this sift down operation, we will still maintain the minimum heap property. So this is pretty much the essence of removing an item from the binary heap. And as you might notice, the time complexity of this operation is pretty much the height from the top to the bottom. So if you perform sift down on the root of the binary heap, the number of operations would be h, where h is the height of a binary heap. In this case, h is equals to log base 2 n, where n is the number of nodes. So this is pretty much the time complexity of pop. Now that we got the algorithm down, let's try implementing this in multiple languages. So now that we have the algorithm down for popping an element, let's try to implement this in Java. So before we do that, let's recap our current implementation of this minimum heap. At the moment, we have the insert method implemented, and this allows us to insert an item to the minimum heap while preserving the minimum heap operation. To recap, we have a maximum capacity that represents the maximum number of elements this minimum heap can contain. It also has a current size, and we also have a vanilla integer array representing all elements inside the minimum heap. We have a constructor, and in the constructor we specify the maximum capacity, the size attribute, as well as initialize a new integer array of the same size as maximum capacity. We define the insert method over here, and the essence of the insert method is pretty much putting a value at the very back of the heap, and we proceed to heapify up this newly inserted value over here. The heapify up method pretty much takes this newly inserted method and compare it together with the parent. And if it happens to have a smaller value than its parent, we will swap and we will recursively do this operation until no more swaps occur or we reach the very top of the minimum heap. We also define a couple of helper methods. Has parent, check whether if a current index have a parent, get the parent index, as well as compare whether if the left index have a smaller value than the right index. We also have some helper methods to swap two items in the heap at left and right index. And we finally have one helper method to express the current heap as a string so that we can quickly check whether if this heap follows the minimum heap property. Before we start, I'll be making a little adjustment. Compare isn't really a helpful name over here. So let's change compare to left smaller. This will hopefully be clearer that we are comparing for whether if the left index have a value smaller or equals to the right index over here. So with that, let's get started to implement our new method, pop. So let's quickly define this new method over here. This will be a public method so that our users can call this method on the instances. And in this case, this method will return an integer representing the minimum value inside this minimum heap. This pop method doesn't take in any parameters and just proceeds to pop the smallest element from the heap. So before we proceed to pop the element, the first step is to check whether if the minimum heap is currently empty. So if this dot size happens to be equal to 0, we can throw an exception, so throw new exception, And we will specify an error message and call that heap is empty. And since this method throws a possible exception, let's decorate it with the throws exception in the function signature so that it's clear to our users that this method can potentially throw an exception and you should wrap it in a try and catch block. The next step is to take the current value at the very top of your minimum heap, the smallest element, and store it inside a temporary variable. Let's call this toPop, and this will be set to this.heap at index 0. We will then proceed to set the last element inside your heap to be at index 1 instead. So we do this.heap.0 equals to this.heap at this.size.heap at this.size minus 1. So this pretty much have the effect of, okay, let me see, why is this throwing exception? Oh yes, just complaining because the function signature doesn't return an integer. That will be resolved later. But back to this, we are setting the final element inside your heap at the very top of your minimum heap as described in the explanation. So once we're done, we will proceed to decrement size by 1. We just pop the new element after all. Sorry, the minimum element after all. So the final step would be to perform an operation called heapifyDown. HeapifyDown, as its name suggests, heapify down the value at index 0, and it compares it with the smaller children of its two. And if the current parent happens to be larger than its smallest children, we will perform this swap and recursively do the same until no more swaps occur or we are at the leaf of this heap over here. So let's call heapify down. And once we're done, we'll return to pop like this. So that's pretty much it. Our next step will be to implement this heapifyDown method, and let's do it over here. Let's define a private void method and call this heapifyDown. As we discussed, heapifyDown is executed on the node at the very top, which was previously the final element. So we will define a current index, and understandably the current index is pointing at 0, which is the topmost element. The next step is to check as long as this current index have a children, in this case has left child, current index. In this case, we choose to check the left child because, as we discussed, a binary heap has a complete property. And what this means is if a parent node has children, it would have a left child first. So we just check whether it has a left child. And if it does, we would initialize a smaller index, which represents the child with the smaller index in a moment, temporarily set to get left child index. So at this step, the next step is to check whether if it happens to have a right child as well. So if we have a right child, then what we will do is we will get the right child index. Just to get right child index, current index. And at this point, we are not sure whether if the left child or the right child is the smaller one. So what we will do is if left smaller, if smaller index, if the smaller index currently containing the left index is not smaller than the right child, then what we will do is set the smaller index to be the right child index instead. This has the net effect of ensuring the smaller index is pointing at the smaller child. And once we're done, we can compare whether if this smaller child happens to be smaller than its parent. So we'll do a similar check over here. Have smaller, and in this case, this would be current index and smaller index. And if the parent currently is not smaller than its children, then we'll just do the swap over here. So current index and smaller index like this. And if this is so, we will also set the current index to be the smaller index in preparation for the next recursive check. Else, in this case, if no swap happens, it means that the minimum heap property is already achieved and we can return just like this. And that's pretty much it for this heapifyDown implementation. As you can see, we have defined 4 methods, 4 high-level methods which we have to implement. So let's do that for now. The first method we're going to implement is to get the left child index. And this get left child index returns back an integer referring the left child index of a given index. So let's call this index. As we discussed in the first video's implementation, the left child index formula is equals to index multiplied by 2 plus 1. So this is pretty much the implementation. The next method would be to check whether if we have a left child. And this left child method would pretty much be very similar to our method for has parent. So remember, in has parent we use get parent index and check whether if it is out of bounds. So similarly in this case we'll be checking that as well. So get left child index is less than this dot size. And that's pretty much it. Oh yes, of course, this is Boolean. And we have two more methods left. Let's do that for get left child index as well. In this case, the implementation is very similar to left child index and has left child. So let's breeze that through. So this would be index multiplied by 2 plus 2. And that's pretty much it. And let's define the final private method has right child. This takes in an index. And this would be checking whether if the right child index is out of bounds. And that's pretty much it. We are done with our implementation for popping an element from the minimum heap while ensuring the minimum heap still maintains its minimum heap property. And now that we have this, let's quickly do a sanity check for whether if this was implemented correctly. To do that, we will be specifying a while loop inside the main method and proceed to pop out every single item inside this minimum heap until it's empty. The expected result is all values inside the minimum heap should be printed out in ascending order. So while this minimum heap is not empty, or rather its size is more than 0, we will proceed to pop this. So we will wrap this operation of popping inside a try-catch block. As we discussed, it's possible to error out. So system out print line dot get message, and over here we will proceed to define the pop. So minimum heap dot pop, and if this pop is successful, we will print out the pop value. Okay, so this looks great. Okay, looks great. Let's try to run this now. First step is to compile this minimum heap. So javac heaps package followed by minimum heap java. We compile this. This is successful. Heaps.min heap. Let's run this. And as we can see, we were able to successfully pop all elements from the heap in ascending order. And that's pretty much it for this pop implementation. So in the subsequent videos, we'll be going through the final method to implement, which is called heapify. And heapify takes in an array of numbers and it moves around the number such that it gets the minimum heap property. This is a very powerful operation as it is able to do this in O(n) time instead of n log n. We will also discuss why exactly is why is it O(n) instead, and we'll go a little bit into the math behind its proof as well. So that's pretty much it for this video, and we will see you in the next one.